started, I felt bad a little bit because I had the impression that I was the one that was putting like the, low note in the sense of saying that we're just doing bad science. So today I thought, okay, well, I want to try to convince you that, there's parts that, came out of that process of trying to deconstruct what consciousness was that taught me a lot about what we were missing in the picture. And the part that we were missing was how much our prior experience affects what we see. And for those of you who are neuroscientists, I started with this picture just to show you that I guess that most of you who know will recognize it as a brain. And of course, if you look at each of the individual pixels, it's not a brain. But we know just because we have seen plenty of those. Right? And what this tells us at the same time is that our perception is really intimately linked with what we know and what we have experienced before. And what is even more interesting is that I cannot ask you to see that not as a brain, which is, like the part that is really striking about how prior experience affects conscious perception. What this also told me is that this gives us an opportunity not just to use, say, the typical variations in terms of, just normal fluctuations in the system between seen and unseen. We can now use a more like engineering perspective because we can use the learning process and the intimate plasticity that the brain has to try to modify consciousness. And by virtue of that, hopefully gain, control over that and modify that capacity and then see how that, emerges as people start learning to see. So I think that, at least in my view, and you may disagree, and it would be interesting to discuss that later on, I think it's good to gain control over the variables that we are trying to measure, and not just, see that, okay, sometimes I see something, sometimes I don't, I have no clue why. And that's why, so the idea of this talk today is really trying to use the inner plasticity of the brain as a way to understand how we can change that and what happens in the brain as a function of that. And I'm going to give you two examples as of what happens when we have a prior or when we have an experience with something. So for those of you who has never seen this image, it's mostly probably just a collection of black and white blobs. But if I do this and then I come back, you cannot stop seeing a frog. This is the so-called one-shot perceptual learning, right? Which is very interesting, is that if I ask you to go back to seeing that as a black and white blob, you can't. I have changed your experience for once. And so this really tells us that there's some kind of unconscious processes that really interact with our perception and change them dramatically. And this can happen just as I did it now very quickly, or as having experience for many, many years with something, right? So for those of you, I guess, well, for some of you who are, probably old enough, who have seen these kind of clocks, if I ask you now to look at the tilt between this clock and that clock, you will probably all tell that, this seems more tilted than the one above. Actually, they have the same tilt. There's nothing different. The only difference is that we have seen those for years and years and years. So this is just adaptation, and therefore, they appear as if they are more tilted. So we have very rapid changes in experience by prior experience, but also just a long history of learning. And I'm going to use those capacities to now try to understand consciousness. And I'm going to try to tackle two questions. So on the one hand is that how do we learn to see and which circuits in the brain may be involved? And the second, which is going to be a probably more like a bigger question, is like, can we understand plasticity as more like a common framework? And in this case, I'm going to try to talk about the Bayesian brain. This is something that Matt alluded before, and we're going to try to say, the case I'm going to try to make for this talk is that the Bayesian brain is a way in which we can understand very simply why prior experience affects consciousness. And in this case, I'm going to try to give you some hints as of how the brain actually copes with prior knowledge. So let's start with the first one. For many years, and this is like a long history of research, people start to talk about perceptual learning. And what it was very clear that if we are exposed to, for instance, certain images, then we can actually become better at certain tasks. And people all the time said, "Oh, this is learning to see," as if actually our consciousness had changed. What was interesting in that experience, in that in those studies is that they never really measure whether people actually learn to see more. They always measure behavior. Say like now people can recognize that something is more tilted or less tilted, but they never ask the simple question like, did you see more? Did you see better? And we yesterday reviewed this case. We know that being able to perform in a task is not the same as knowing or as seeing. And this is something we know from cases such as in blindsight, right? So these subjects that have lesion in B1, they can do fairly complicated things. So they can localize stimuli that they don't see. They can identify stimuli that they don't see. They can detect. But if you ask them once, repeatedly, they will always tell you, I don't see them. I just, my brain somehow can point, can do these complicated things, but I don't see. So knowing and really seeing are two different things. So the first thing that we asked in this case was, well, can we try in normal observers to push the threshold of perception? Can we make somebody to see? Right? And this is, it's kind of like a naive question, but when we started doing this research, people thought that actually perception has a fixed threshold. So you could just show stimuli again and again and again, and nothing will actually ever change. So we thought, well, what if we just, ask college students to do these experiments for 5 days? They come to the lab, we show them these images, we present them first this rhomb or a diamond, and we present a mask later on. And by virtue of doing that, if you actually manipulate the time between these two, you can actually make that rhomb or that square to disappear. And whenever the students would come to the lab, we would titrate such that they would not see at all. Right? And then now we would tell them, like, you know what? You're going to just see these images. We're going to ask you all the time 2 questions. The first one is, tell me where you think that it was a square or a diamond. This is the so-called discrimination task. But I'm going to also ask you whether you see the image or not on a trial-by-trial basis. And we did this for, as I said, for 5 days. And what we observed is that if we look at sensitivity, so how well they did from the very beginning when we showed them these seemingly invisible square and diamonds up to the 5 days, they did fairly well in the post-learning session. So they could really discriminate the square versus the diamond. They could also say at the end of the 5 days that they had seen the stimuli more, right? So these two mechanisms or these two behaviors seem to actually increase in parallel. So we thought, well, do they depend one on another? So could it be that because I was better in saying square and diamond, therefore I became conscious? Or could they just be dissociable, right? From the blind side, we would say they are different. So the fact that I can see something doesn't mean necessarily that I can perform the task. And if we now look at the learning curves, so this is how well they would do on the first day, the second day, the third, the fourth, and the fifth. And this case is whether it's seen or unseen. What happens in the first day is that regardless of where they saw, they didn't see the stimuli, they did really, really well. So that's a hallmark of blindsight. So it doesn't matter where in fact, they did not see it, and they did really, really well in telling us where it was square or diamond. However, that behavior went away as time went by. In the second session, they would only perform well if they saw the stimuli. And this would also happen the third day, fourth day, and the fifth day, right? But in the first day, they were just like a blindsight person, right? So this is the first hint that, seeing a square or a diamond has nothing to do with really seeing. The next thing that we did is that you can exploit a very basic property of the visual system, that it has receptive fields. This means that there is a part of the world that maps into our B1 or into our B4 and so on, and they have different sizes, right? So now in the very first session we put the stimuli here, and this is more or less the size of the receptive fields that would cover B1 and B4, right? But now if we move this stimuli here, it would actually map onto receptive fields that are actually far bigger. So we could now say if the performance transferred to this new location, we could say, oh, it has to be a receptive field which is as big as this one. And if it doesn't, it has to be receptive fields that are actually smaller, of the size of B1 or say B4, right? So now what is neat about this is that this is purely psychophysical measurements. but you can infer which areas you had trained. So when we move the stimuli here, we observe the following. In the case of the learning sensitivity, so tell us where it was a square or a diamond, subject did really poorly. They went, they were as bad as when they started the task. And this is a learning curve of one subject, it was a research assistant, so she was very motivated. So she did this for 21 days, right? And after the 21, so she became, every day she was better, right? But then we moved the stimuli and poof, gone. So we know by that we must have trained these receptive fields that are actually smaller than before, right? What was super interesting is the following. Visual awareness stay high, which means that the receptive fields that we must have trained for learning to see must have been different than the ones that we trained for learning to perform. And this is, this is psychophysical evidence. It's interesting, but you would say, well, I don't believe you. You just show me some brains, and then I will see, right? So we did we took that serious, and now we repeat the very same experiments in the MRI, right? Again, subjects, had to learn for 5 days. And we ask in this case, which one are the areas that increase their activity as a function of only learning to see? And we observe that is temporal areas and occipital areas. We also did the so-called retinotopic mapping, which is that now you can go to B1, B2, B3, and B4, and now see which areas you may have trained. And what we observe is that much like, as I said before, for the visual awareness, there was no change in early visual areas for learning to see, for the subjective perception. However, we observed a huge increase in B3 activity and in B4 activity for learning sensitivity. So in this case, for learning where it was square or a diamond. And this was specific to the area that we had stimulated, because we also had collected data on the area that we showed the transfer, but we had not stimulated, right? So in this case, it only increases activity in that part where the stimuli was. We also observed, when you look at the whole brain, which other areas increase for performance. And we observed in this case it was the medial wall as well as the frontal area. What is interesting is that it's two things. A, the networks are different, and B, these networks, for those of you that were in my talk before, are the typical ones that people find whenever they suppose to investigate consciousness. But also those are the very same areas that relate to decision making. Right? So it could just be that, subjects became better at, deciding between one or the other. Okay? So now the question is, okay, we have these two networks, right? The question becomes, do they interact somehow? Does it mean that because I was better in the square diamond task is because I learned to see? Or the way around, is because I learned to see that I can perform the other task? Or could it be that they are completely independent networks? And a way to look at that is to look at the correlation and activity between these two networks. So now what I'm showing you here is in blue is the so-called objective network, so the areas that had increased their activity as a function of learning the objective task. And the green is the ones that have increased their activity as a function of the subjective task, so when subjects learn to see. And this is how much they correlate at the very beginning, in the first day of the task. And this is how much they correlate after 3 days of training. So they really appear super intermingled. So then you could say, well, they are actually one and the same, right? And when you look, there's a really linear correlation, beautiful, between the increases in one network and the increases in the other network, right? But I had shown you before two things that seem to actually disprove this idea. One was that we had line set at the very first session, so it seems that there is a dissociation. And also with the transfer task, I show you that one remained there, so we could generalize, whereas the other one didn't. So how could we solve that puzzle? And we thought, well, there is a very simple idea here. So imagine that actually you had two networks, but they are both connected to a common input. If that input gets better, of course, both networks will get better, right? But it's because they actually share a common input. And that actually is not that weird to think about because of the following. So if we look in this case, this is the proportion of correct responses as a function of exposure of the stimuli. And you can think that this is a proxy of how much information gets into V1, right? And what you observe is that the performance increases. This is only for the seeing trials, linearly as a function of how much we present the stimulus. It's a function of how much information there is there. So we thought, well, this may lead to this kind of model, very simply. We have B1 input, we have some kind of noise into one network, it gets into the objective performance network, we have another channel that also has some noise and maps into the subjective experience. But if we increase this, of course, the correlation between these two will seemingly appear as if it had increased. So a way to look for that is now you can control, when you look at the correlations, you can say, okay, now let's parcel out the activity of this area, right? And if you parcel out the activity of B1 in this case, now there is no correlation between these two areas, between these two networks. So it seems that it was all driven by B1 activity. And we know furthermore that we had activity from B1 in the area that we had trained, as well as in B1 from the area that we had not trained, right? Now, what this shows is that if you look at the untrained location, there is a lot of activity. But if you look at the trained location, taking into account B1 activity, there is virtually nothing. So what that also tells us is that it's specific to that area in B1 that we had trained. So it's not everywhere. So just to summarize, I hope that I was able to show you that, I think we have compelling evidence for the fact that the threshold of perceptions are not fixed. We can change them, and subjects may find this boring, but because the task is actually not particularly exciting. But we can actually show that subjects can learn to perform better as well as to see more. That these are two dissociable functions that share a common input, and that the networks that actually we train are completely different. And I think this is actually fairly relevant because if we think, in the case of the blind side, a therapy that would relieve the pain would have to train the subjective experience and not just the performance, because they can perform better. So we actually have to tap on something different. And this is just, I'm going to go back to what we discussed yesterday. And I think that using learning is a fairly good tool to try to get at distinguishing the precursors from the consequences. Because we don't think that the precursor and the consequence may change at the same rate as as the subjects become conscious. So I think that this is another way in which we can dissociate the real correlate of consciousness from the ones that actually are not relevant. And now I'm going to switch gears, and I'm going to try to convince you that maybe understanding prior experience in a broader context, in this case in the Bayesian brain, would give us a clue about how we just navigate the world, and how we become conscious as well. And I guess that most of you actually are familiar with the idea of the Bayesian brain. The idea here is that we are not just reacting to the world. We are always having expectations, priors, and it's the combination of these priors plus the sensory input that actually leads to perception. And to give you a very intuitive idea, if I show you, for instance, this image, you may actually see it very well just because you can see the non-masked image, right? So in this case, this acts as a prior that allows you to see way more than in the case when the image is degraded. And this is something that happens all the time that we may not really be completely aware of. But when we look, for instance, at language, and I present you the C-level pa and ga, right? There is many different speakers, and it's very many different people that actually would say that. And the thing is that if you actually look at the signal, there is no difference sometimes between the pa and the ga. But in our mind, they're actually very, very different. And this is the so-called categorical perception. So it's us who have a model in our brain that says, you know what, I think that this input must have been this pa, and this input must have been this ga, right? So the point I'm trying to get at here is that this tells us two important messages. A, that perception is constructive, because it's because of those priors that we construct a model and we end up perceiving, but also that perception is categorical. And this is just because we have constructed those models. Now, the question is, how do we learn those priors, right? Like, does it take us, forever to learn those priors, or is it something that, we could learn in very few instances? And I'm going to give you two examples as of, how quick we can actually get at that. Do you get it, right? Isn't that interesting? Like, I've shown this video, and I know how many audiences. Everybody gets the sequence, right? And it took us, how long? It was like less than a minute. So this is what we're really, really good at, extracting patterns, extracting regularities. So this is the default mode of the brain. But also, it's the default mode of the brain to recognize when those patterns are just wrong, right? And this is an important thing because we need to learn when things are not the way we expect them to be. So we have to have, on the one hand, a mechanism that would extract those sequences, as Matt was saying, those patterns, but also a mechanism that would tell us, what? Your model was wrong, so you have to update it. I'm going to give you now the next example so then you see like how quickly also we can recognize the deviation of the pattern. It's an impossible task, right? So you couldn't predict what it was going to be, right? I'm just giving you these examples to really show you, to illustrate 2 points. So A, that the brains are really, really good at doing this. And we do that all the time. It doesn't cost us anything. We don't feel tired. This is just the way in which we, by default, operate. And this had actually led people as, well, all the way to Helmholtz, but these days, Carl Friston, to postulate the idea of predictive coding. So what they are saying is that they are kind of like trying to say that, let me just give you this. The analogy would be like something that the brain is like a scientist. So every region higher in the hierarchy is trying to predict what the regions in the area below is seeing. It's a little bit what Matt was saying with getting the autocorrelation model. So instead of actually really trying to capture what the world is doing, every region is trying to extract a model and say like, oh, how likely it is that I actually had seen this. And this is something that occurs in every area. What is also interesting is that, so in this case, you always have feedback that goes from higher areas to lower areas that conveys the model, and this is linked with the sensory evidence. And it's only the deviation that actually gets transmitted. And you think that, if the model was perfect, and it could account for all the sensory evidence, it would transmit nothing. The only thing that you transmit is when there is an error. So all that we cannot account for. What is also interesting about this model is that it has a very specific flavor as of which areas, which layers should be doing what. So in this case, the middle layers send the priors to the superficial layers. This is in the superficial layers where we compute the subtraction between the sensory evidence and the prior, and this is what in turn gets transmitted. So in essence, the prediction errors should be seen in the superficial layers, right? So it's a very detailed model. There is a lot of fMRI, say evidence for this, but as you can think here, fMRI is probably not the right tool to really, test this model. So we thought, well, why don't we try to revise this model under the following question. So on the one, in the predictive coding model, we actually have 2 terms. We have, on the one hand, the prior, which is the model that we would have, the prediction error, which is how different the information is outside from what we had predicted, but also the model update, which is like if the model is just wrong, we have to generate a new model. So now every time people in the fMRI looked at the so-called like prediction error signals, we don't know where we're measuring prediction errors or model updates. So we thought, well, why don't we try to look at that in the context of ECOG? So in this case, these are electrodes that people have in their brain, right? These are patients that have epilepsy. And we look, and the idea now is to look at, can we actually distinguish areas that would contain the prediction errors versus the ones that would contain the priors and the ones that would contain the model updates. And what we did in this case was something very simple. We present, in this case, 4 syllables. The first 3 would be always the same, and the 4th would be different, sometimes, very seldom. But it would be different in 2 conditions. So either something where the subject could recognize a difference, because it was different categorically, or the sound would be different, but the categorical perception would make as if it was the same, right? So you can actually dissociate what is in the stimulus versus what is in the brain, what is in the mind. And these are one of the really, fantastic things of working in NYU in the epilepsy center there is the electrode coverage that they have. And because it allows us to really understand the brain with a detail that is very uncommon. And these are, we measure in this paradigm 10 different subjects. These are the electrodes that each of them would have in their brains. And this is how it looks if we put all the electrodes together. So we have a very good map of the implicated areas. And the first thing that we looked at was which one would be the areas that would have prediction errors. So that would have reductions in responses as a function of the model being good, right? And in this case, these are all the areas that reduce the response. So in this case, if we present like the pa, so it's the same stimuli all the time, these areas would reduce the response importantly. What you cannot really see it really well, but behind that red line is the single trial responses, just to show you how systematic. Can you see it better? Yeah. How systematic that response is. So these are all the areas that, as a function of showing the very same prior, would reduce the response proportionally. And they cluster around the STG. Remember, these are syllables, so it's where you would expect them to be. Also in the motor cortex. And what is even more interesting is that we found out that despite the fact that their responses would lower, the information that they would carry would be higher. Because now what you can do is that you can run a classifier on the non-adapted responses. Say, can I distinguish between a pa and a ga when the responses are very high? Or can I distinguish the pa and a ga when the responses are very low, right? And what is interesting in this case is that the classification is better despite the fact that the responses went down, right? So there is more information even though the amplitude was low. The next question that we asked in this case was, well, can we distinguish between the prediction errors and the prior updates? And the signature for that would be the following. So in this case, we look for areas that would increase the response for the first stimuli because if there was no prediction. It would reduce as a function of being the very same, but it would go up as a function of being a new one, right? So in this case, something like pa, ga, right? So those areas would have prediction errors that would reduce, but also would go back once you cannot predict. What was interesting was this other set of areas, that had 0 responses to any of the stimuli and would only respond whenever something was different than what they had expected. So these are truly model updates areas. So they don't respond at all to the other. What is really interesting is that these two areas are intermingled in time. So it's not that the model update electrodes or areas are they are activated earlier or later than the others. They are really at the same time, and they are also not separated in topography. They're just more or less around the same areas. What is also interesting is that we looked at whether this was dependent on attention. So could it be that the subjects, because you could say, well, the model updates may only be there if I am paying attention, right? Otherwise, I don't have anything. I don't have any model in my mind. Well, we withdraw attention from the very same stimuli, and the subjects would completely not get the pattern. But in this case, the responses would actually be the same. So we would have areas that would have these prediction error responses, and these others that would have these prior updates. So being attentive or not being attentive doesn't really matter in this case. The brain just automatically would extract those patterns. Finally, this begs the question: how do these areas interact? Right? If they interact whatsoever. And at least in the predictive coding account, what you would expect is that if you have a model, this would allow the brain to, on the one hand, generate the subtraction between the sensory evidence and the model update, right? And then it would actually pass those onto the next areas that would actually have to update the model, right? So in this case, what we would predict is that the direction of the information transfer would change depending on whether the prior is good or the prior is bad, and we have to update it. And we looked at, in this case, Granger causality, and we looked at what happens between the so-called prediction error electrodes and the ones that we call prior updates for the case of the standard. So in this case, when we show all the time like pa, So there was nothing, in this case, the model that we had was sufficiently good, so we didn't have to update it, right? Versus the one where the model was bad, and we actually had to update it. And what this in turn entails is that if the model was good, then these electrodes would have an influence on those, and if the model was bad, then now those electrodes would have an influence on those, right? So in a way, the prediction error electrodes make the model to be updated only if the model is wrong. And lastly, we had the great opportunity. So in NYU, this is an experimental technique, but we are allowed to implant laminar electrodes on patients that have epilepsy. So now we can look at how the different layers in the brain, in the humans, would behave in a task like this one. And we had the opportunity to implant those electrodes in 5 subjects. We don't control where those electrodes are, right? So the idea is that you would actually implant those electrodes in areas that are likely to be resected, because we don't know where we are causing any tissue damage. So the electrodes just get somewhere, right? And in some cases, we are lucky enough. So I'm just showing you an example here where we have 2 ECOG here, and the laminar electrode is in this place of the brain. And as you see, the red electrode shows these prediction error responses. But the gray electrode doesn't show anything, which would be this one. So we're lucky enough to have the laminar electrode close by to the ones that actually was having prediction errors. And what we observe in this case, this is a current source density. So in this case, the way in which you have to understand this is cortical depth from superficial layers to deep layers, and this is time. And this is when we present either the very same stimuli, so in this case, A, or pa, versus when we say pa, ga, right? And what the predictive coding hypothesis would predict is that the prediction error signal should be the highest in the superficial layers. And this is, in essence, actually what we observe. So these responses that you observe here are higher than in this case, and these are actually in superficial layers. What is very interesting is that they are only there if the subjects notice the difference. So in this case, when I show you, when I have categorical perception working there such that the subjects cannot notice that, it would appear as if they were standard, right? So the very same amplitudes in those regions. And this is an example electrode in one particular patient, but this is what we observed across 5 patients in which we had this technique. So in all of them, the responses, the difference between the predicted and the unpredicted was the highest at the superficial layers. So I hope that with this, I had provided you some evidence that it seems that the predictive coding framework does seem to work. So we actually do observe prediction error responses. They do appear in the areas of the brain where one would have predicted. They do also appear in the layers in which the model had predicted. And now the question is, do they have any behavioral consequences for consciousness? Right? And this is what I'm going to try to convince you. I'm going to try to show you for the very last part of the talk. And what is relevant here is that these priors are actually unconscious, right? So it's not that you are aware of them. You may be, right? I'm not saying that you're not, but the point is that they will change your perception no matter whether you are or you aren't, right? So now that begs the question, how could an unconscious process affect a conscious stimuli? And this also entails some more questions like, which aspects of the perception it will affect, the content, the timing, the quality, and are these effects perceptual or post-perceptual? What this means is that you can also think that it's not changing your perception per se, but it's just you are deciding differently, right? So it's, in essence, the quality hasn't changed, but you are just making a different decision if you have a prior. And this is, I'm going to just rehearse a little bit what we showed yesterday. So we had this paradigm where we ramp up a letter from not seeing anything to seeing completely well, and then we degrade it again. And what we observe in this case is that the threshold of perception change as a function of just having the prior. And I showed you yesterday that the correlates of perception also switch by 100 milliseconds. Right? What we then wonder was, well, if it changes by 100 milliseconds, how could that happen? And and we saw that an intuitive way to try to look at, whether the brain would now be able to accomplish that because it's sampling the information differently was looking at eye movement. And the idea here was actually very simple. So imagine that, you know nothing. So your space of possibilities is endless, right? So you can think that, like I'm seeing this face or that face or that face, I know nothing. But if I have a prior, now I actually reduce my search space. And that's why the brain becomes faster. That's why the brains become faster. So in this case, we divide stimuli. Imagine like this is like a frog. We remove the contours, and now we can actually look at which one are the areas that have maximal information. And we now let the subjects move their eyes and explore the images, right? And the question was, okay, how would they explore when they know nothing versus when they know everything, right? And this is their patterns of eye movements when they know nothing. And as you see, they're actually fairly scattered, right? But when they know, they A, have far less eye movements, and B, they tend to actually go to the areas that are maximally informative. And now we can know that because we know which areas we know by construction of the stimuli contains the most diagnostic information. And this is exactly the places where the subjects fixate. So they become actually much more efficient. And we think that this is the way this is the reason why the brain became, or the correlates actually became faster. It's just because it has a very good hypothesis. It doesn't have to explore everything. Second, the question was also like, how are those priors? So I just showed you that, okay, we have those priors. It makes us to see better. It changes the timing. It changes our patterns of eye movement. But now that begs the question, like, how are those priors embedded in the brain? And how are they combined with sensory evidence such that they boost our perception? And one thing that we repeated the very same experiment that I showed you yesterday with the letters in the magnetoencephalography in this case. And we look at the so-called like alpha activity. And we looked at that because some people believe that slow oscillations contain priors or contain, feedback information, right? As compared to, say, like gamma oscillation. And in this case, what I'm showing you is this is the activity before the stimulus was presented, but it's just the difference between when we go up and down in the curve. So if there's nothing, there shouldn't be anything there, right? Because in essence, this is the baseline. I haven't shown anything to the subjects, right? But contrary to that, we observed that the alpha oscillations were higher when subjects had a prior. And they were higher in the very same electrodes in which the activity then would be higher when the stimulus was presented. And this is actually the activity that then led to the boost in visibility. So in essence, by virtue of that, what we think is that, let me just show you. What we did is that we can actually look at the activity in the baseline and see which one are the areas that contain those priors, right? And ask, are they the same areas that have increased activity in the baseline when nothing is there, the ones that have an increased activity when the stimulus is there? And actually, they are the same, right? Which is, you can see here, occipital cortex and temporal. So the idea here is that probably, and I'm not saying that this is, this is just a tantalizing evidence, that probably alpha oscillations in those areas that actually are encoding information do orchestrate the activity that then, or maintain the priors online. And finally, we asked the question, when do these priors change perception? Is this post-perceptually or at the level of when the stimulus actually comes in? And we ran the very same experiment that I showed you yesterday. So we either manipulate the prior knowledge or the sensory evidence. And let me just go to the important information. And what we observe is that in this case, we run a correlation between those subjects that had the highest gain in visibility with the maximal changes in their brain responses. And we ask at what time that correlation exists. And what we observe is that around 80 milliseconds when that correlation is the highest. Right? And we think that because it's so early, that it has to be perceptual and not post-perception, not decisional. And what is also interesting, I guess for Matt as well, is that this is mostly in the retrospinal cortex. These are the areas that seem to actually be activated the strongest when subjects have that prior and when the perception actually is boosted. Just to summarize, so I hope that I was able to convince you that on the one hand, prior experience does boost perception, and that it that it does so by, on the one hand, changing the way in which the way in which we sample information, and probably that is what entails that the brain becomes more efficient. Right? And also that the perceptual inferences takes place in this large-scale network, and it's probably just a machinery that's there all the time. This is the idea of the Bayesian brain, and that these prediction errors are computed, mostly in superficial layers. And this is the information that is transmitted to the next area. And I think with that, I just want to thank you and all these people that are in that picture for helping us in writing those studies, including Marcela, who is sitting there in the audience.
Questions? The error detection you show us make me think about the efference copy in the motor system. Comments on that? Because they look pretty similar.
Right.
So I don't know if you think it's the same mechanism for both process,
yes.
or I don't know.
I mean, the idea behind the Bayesian framework is that the efference copy is just another prior that you would actually have, that the system would actually have, right? So in that sense, it's not necessarily different from just having a prior given by memory, for instance. Right? The question is, how are those priors set up? And that we don't really know very well. Pedro and I are working on eye movement task, and so what we do know, for instance, is that if somebody moves their eyes, this generates signals that kind of like preempt the whole visual cortex, and that actually makes the information to be processed differently. So there seems to actually be evidence that the motor command actually does have an impact on, and it's probably of the same kind of this kind of stimuli, right? Or of this kind of things. Whether there is differences at the same time, I don't know. Maybe I don't. I mean, it could be, right? Because of course the specificity of the motor priors is fairly different from the specificity of the priors done by memory, right? So when I say, for instance, retrieve an A, it could be like a very big A, a very small A. It could be something they say, something that you see. Whereas in the case of the motor cortex, something very, very specific. You expect something, of this sort at this point and nowhere else. So maybe they just have different levels of specificity.
Thank you for the presentation. In respect of blindsight people, when they can move toward a space, they can catch objects and so on, there is any correlation that they can express about any kind of experience, maybe an intuition or whatsoever, with the space? I'm asking because when somebody is blind and there is some prostheses that they're being implemented experimentally, they can learn to have some kind of experience of the correlation of electrical or mechanical input with their own proprioceptions and movement in space. So there is some kind of whatsoever experience you can know or have investigated about blindsight people?
Yeah, I haven't worked with those subjects myself, but I think that's a very good question because I'm not sure where you need consciousness to actually use that proprioception, right? So you could think that if you don't have awareness, then you may not use all those cues, right? And that actually could be a possibility. I don't think that, for all that we know, subjects don't use that. Like they very often, if they would use or exhibit blindsight behavior if you force them to do it, right? But, if they're thirsty and the glass is there, they wouldn't really reach it, to the glass, right? Unless, say, okay, you know what, just try, and you kind of like force them, right? So somehow, by some means, they cannot really use that information. So I think that you may need awareness to actually guide behavior.
Hi. I really like the idea of this predictive coding. However, on the way you portray your model, it looks like a sequence of layers, which is completely against our idea of this complicated network. So the flow of this predictive coding is something puzzling from that point of view.
Flow in which case? In which way?
You mentioned that the higher layers will sort of trickle down the error signals and so on. But that requires a particular sequence that will work well if you have a very strong hierarchy of areas, right? Yeah, like that one, you know? And so, but I'm not sure whether this is really true of the architecture of the cortex, where we really don't know where it's up and where it's down.
I mean, there is some, I guess that, you're thinking of, say, subcortical structure that somehow, like, don't map really neatly into, I agree with you. I mean, this is a very corticocentric view, right? So if you think of, say, B1, B2, B3, and so on and so forth, and the hierarchy actually does seem to hold, right? But it's very corticocentric. And I think that the model is really lacking, having the hippocampus there, and all the subcortical structures, right? So you're totally correct. There is people trying to think about those, for instance, for attention. And now they are thinking that the pulvinar is one key relay area, right? But of course, all the others are not being taken into account, right? And I'm not saying that this is the proper model, we just said, okay, if this were to be the proper model, at least we should see this kind of activity. So I'm not advocating for that model in particular, but I think at least we have evidence that this model is not wrong, just plain. Right? But,
I would say to you, thanks for your presentation. It's very interesting. Yesterday we were talking something, and I wonder if you have a prior experience with enough intensity, you can develop a trauma.
Right.
Yeah. And after that, you have a similar experience, and the adaptive capacity of the brain must be, how do you say, overcome. And if we think the brain go to the past, analyze the information, and come to the present, in terms of physiology, the time doesn't exist for the brain.
Right.
Yeah? That's why I thinking in the patient of trauma, because I'm a doctor, I want to treat the pain, the emotional pain, the pain. If you put an image, if you put a new context, you can resignificate the past. You can change the past.
You mean?
I mean, in terms of physiology, of course.
I don't know. I mean, there is people. I think that Daniela Schiller actually has been working on, whether by if you remember something in the past, whether you can actually change that memory, right? And that seemed to actually be the case. So it seems that memories are not, like it's not that you have a picture and then that's going to be forever the same way, right? So memories can be changed as a function of retrieving them, right? So
but if you change the memory, you change the physiology also.
Right.
If you change the physiology, you can cure the symptom.
Yeah, absolutely. Yeah. I'm not sure when you can change the past as such.
No,
the things were the way they were, but you can resignificate.
But what is the past? Yeah. The past is your context, your emotional context, your cultural context. That's why I ask.
Right. That's true.
Thanks. Nice talk again. It's a question about the perceptual, if the last thing that you mentioned, if changes are at the perceptual level or at the post-perceptual.
Right.
So it's kind of like a logical, conceptual question. What would be the purpose of modifying the perceptual level if you have already made the right distinctions at the post-perceptual level, and you keep going, you know? Like, I don't see why the architecture will be like, will be such that it will have this feedback up to the perceptual level. So to make it more concrete,
so maybe.
I can give you an example. So say that someone says to me, let's go to the car. It sounds very similar to let's go to the bar.
Mm-hmm.
Okay. If I have prior knowledge, I am with a friend, and probably after the conference, there's more changes that we go to the bar, you know. So, well, say that's what. That let's go to the bar, the place where you drink. It could be that I listen car at the sensory level, but because of the prior context, I activated the category bar, the B. And I don't see the purpose of having this kind of feedback and modifying the sound again.
Mm-hmm.
Why the brain will need to do that? You know?
I guess that the question is, you can think of a system where the information, the sensory information is not altered, but you alter at the end the decision making. It's like, you know what, I think that it was bar as opposed to car, right? Alternatively, you can think of a system that at the very beginning just heard car, and all the other possibilities are just not there any longer. This is what we're trying to, that's the distinction that we're trying to draw. So did it actually change the way in which you perceived? And it's like, it's the same question, you know, with attention. Do you have the bottleneck at the very beginning? Or you have everything, and then at the very end, you choose one element among the others, right? The evidence that we have here is that it seems that the brain or the system actually is such that it has such a strong prior that it biases you to perceive things one way, such that you cannot perceive them in any other ways, right? So now you don't have the capacity to say bar and car at the decisional level. You just committed at the level of the perception. Which you always have, right? So that's the idea of categorical perception. So you could always say, like pa or ga, right? But you heard only one alternative. You don't heard two.
You have to solve the competition. You have to choose one. You are doing that when you are comparing at the post-perceptual level. Okay? The question is, why you send the feedback to this level?
I could, like, let's take it offline. The idea is that, you don't do it post-perception and then you send it, like back. You do it at the very beginning. So, the decisional stage, which is later on, already has only one kind of information, not two. That's the idea.
All right. Thank you so much. No, let's continue later because we're running.